Alright, my name is Noah Judy, and this is my Physics Lab 6 Magnetic Molasses Lab Report and Data Analysis. Introduction. This experiment involved putting a bar magnet through a tube lined with aluminum foil to observe the magnetic forces at work. The coding aspect was us creating a computational model showing the interaction of the magnetic fields of the bar magnet and the foil tube. And the purpose of this lab is essentially to just observe the magnetic forces at play here. And here's a quick preview of our results. This is just a graph displaying the relationship between time and the velocity of the magnet as it passed through the tube. System versus surroundings. The system is obviously what we're observing, the bar magnet, and surroundings being everything else, including the earth, nearby objects, and primarily the foil tube. So our main principles here are just the forces of gravity near the surface of the earth, F equals mg, and also this big equation on the right here, which is just the equation for magnetic field as a result of distance, with m being the magnetic moment. Here's another equation, magnetic flux, and then velocity and position update. It's a bit of a throwback. I don't think that needs any explanation. Okay, an experiment. We surrounded a cardboard tube with a layer of aluminum foil and dropped a bar magnet through the tube while recording the time it takes for the magnet to pass through the tube. We did this 5 times. Here's a picture of us doing it, and here's a table of our recordings. We found the average time, fall time, to be 1.26 seconds. And here's our glow script model. These are our initial conditions. And then here are our calculations. We got the dipole movement and the flux. And then here we have gravity. And this is what our coding output looked like. This is our model. It's just a tube with a magnet. That white thing up there is the magnet. And then here's our graph, which I've already shown, displaying the velocity of the magnet over time. Comparison. So our our actual recorded data, as I've already said, the average fall time was 1.26 seconds. However, in our simulation, we found it to be 1.134 seconds, and we have hypothesized that this is a combination of several factors at play, including imprecise measurements, operator failure when using the stopwatch, so either hitting the stop button too early or too late. Air resistance within the tube is always going to be a factor, and also friction between the bar magnet and the inner walls of the tube. That's what we think was the biggest one here at play. Some further questions. What is the resistivity of the conductor? What if the resistivity of the conductor were reduced as close as possible to 0? And how would the dynamics of the falling magnet change? So we got to remember Ohm's law for this one. So essentially, high current is going to create a stronger magnetic field, and thus it's going to exert a stronger force against the bar magnet as it falls, resulting in both a slower speed and a longer fall time. Another question would be, what if holes or slots were cut or drilled into the tube, and how would this affect the ring currents in our model? Ring currents would be disrupted, and any asymmetries would create a torque, which makes the magnet spin while falling, which obviously didn't happen. And that has been my Lab 6 report and data analysis. Thank you.